Near the shores of Cayuga Lake, on the East Hill of Ithaca, New York, stands Cornell University and the Cornell NanoScale Science and Technology Facility, CNF for short. Since 1977, the CNF has been an internationally recognized user facility supporting a broad range of nanoscale research, going from biological applications all the way to quantum science. With over $60 million in state-of-the-art tools, a technical staff with over 500 combined years of nanofabrication experience, and our unique mission of working with any person in any research field, the CNF aids anyone in transforming their big idea in the micro or nanosciences into reality.
In the long run, what we're trying to do is to create a system where we can grow biological components that could be useful for human health. We'd like to be able to harvest therapeutic proteins and grow them in a system that doesn't require cell membranes.
My collaborators at Cornell have been building very small autonomous computers. And my lab is interested in turning these small devices into robots. These robots would be able to move, they'd be able to sense their environment, measure things like the voltages or the temperature of their environment, and then report that back to the outside world. On each one of these wafers that we manufacture these robots, we can get 10 million of these devices, each the size of a cell, costing about a penny a piece, and with the computational power of the spaceship Voyager.
We're working on the next frontier to develop hardware for 6G communication systems. I imagine 6G as well as Internet of Things will profoundly impact how we live, how we view information, how we handle our health, as well as the environment.
Motes are tiny silicon sensors that you can put into the brain or other nervous system. They are microscale, that's the M. They are optically transduced, that's the OT, and that's because they're powered by light and they communicate with light. And then they're electrodes. They measure the electrical signals of the brain. They are very, very small, so they can essentially free float in the body without disturbing the tissue around them, because they're so small they just kind of move with the tissue. Basically, when you insert them, things just get out of their way rather than being torn, and so they do very little damage on insertion. Once we have motes working for the nervous system, which is a pretty hard challenge, we envision many other sensory modalities we could work in, including electrochemistry, sensing things like light and sound, but pretty much anything you can sense with electronics, we could potentially sense with a mote.
Our goal is to teach new users how to do research at the Cornell NanoScale facility, to become experts in the use of the tools while taking full advantage of the vast experience of the CNF staff, and ultimately to become purveyors themselves of nanoscience.
Integrated circuits have been made very small. The computer industry has basically driven all of the semiconductor manufacturing to almost the scale of atoms. That part is not so hard. What's hard is to figure out how to attach legs or little flagella that would make these computer chips swim or locomote through their environment. The toolkit we're developing essentially consists of atomically thin films. When ions absorb to their surface, they exert stresses that bend the film. We control that absorption with voltages that we apply to the film. And so as we tune the voltage, the device can simply bend back and forth. That gives us the ability to connect these, what we call bimorphs, to the computer chips that are controlling their motion.
The chemical processes that happen inside a living organism are really complex and intricate. And so in order to recreate those outside of a living system, you need to be able to have control over the design that you make that will carry out and control the order of those reactions. Having a facility like the CNF allows us to take advantage of their tools to recreate these intricate processes on chip. What's really nice about using a microfluidic approach is that we're able to design those using photolithography into all sorts of shapes, chamber sizes, networks that allow us to recreate those chemical reaction pathways that are faithful to the living system.
In order to take factory manufactured circuitry and chop them up into little tiny mote scale things, with optics on top of them requires many machines from the CNF, particularly one called the Oxford 100, which we use to actually chop out the little tiny bits of silicon, as well as others to coat and encapsulate it to mount things. All these operations are all CNF operations.
The tools that we're using at the CNF are state-of-the-art. The CNF is giving us the advantage that we can develop these materials in a research environment. Once we get these recipes, other folks across the country, other scientists could manufacture similar devices in their clean rooms.
The electronic materials we work with in the lab have their unique properties, but more importantly, we need to harvest those properties. And that's where CNF comes in. Our students work really hard in patterning, in deposition, in connecting one function to another function on the same chip. For example, in order to make the smallest features, we use very often electron beam lithography. Those are the smallest knives you can think of to cut a few nanometer of features. They're so small that you can only see them under electron microscopy. CNF staff has been amazing. Whenever I mention I'd like to bring a different element or different material into CNF, they will say, let's look at this together. I will make this work for you.
With all the amazing research going on here at the Cornell NanoScale facility, we attract quite a lot of attention. We host well over 200 visits each year from more than 3,000 visitors. Groups come to the CNF from international laboratories, industry, prospective graduate students at Cornell, and many local and not so local colleges and high schools. We also hold a twice-yearly short course in technology and characterization at the nanoscale, the CNF TCN, and an annual users meeting that showcases our researchers, both of which are open to the public. We enjoy being part of so much outreach because the K-12 visits are our special way of encouraging the scientists of the future. At CNF, we also help companies to achieve their vision of nanoscience.
Currently, I serve as the CEO of a company here in Ithaca. We've partnered with CNF throughout our product development. CNF provides us the resources in terms of the staff, as well as also the machines that we need to advance our product development. I did my PhD in electrical and computer engineering, and based on the knowledge and skill set that I got from Cornell, I'm able to assemble a team of engineers and advancing our product to the market.
I'm an alumnus of Cornell University. I did a PhD in physics. We founded a company in 2000 that was originally called Nanofluidics, but is now called Pacific Biosciences. The foundation of the startup was based on technology that we first implemented in the CNF. I think it's hard to overstate the importance the staff had. There's really a strong educational component to their presence at CNF. And I think it's fair to say that without the education that I received at CNF, that many of those ideas may never have even existed.
The future of nanotechnology can go in so many directions, and here at CNF, we are uniquely positioned to have an enormous impact on the science of tiny things.